So the next topic that we're going to be looking at is curvature, the normal vector and the binormal vector. We'll start out with curvature. And so the idea of curvature, or the curvature of a vector-valued function, is a measure of how sharply or how smoothly a curve turns in space. So if the curve turns sharply, its curvature is going to be higher at that particular point. And if a curve has a more gradual turn, then the curvature is going to be lower at that point. And we're going to utilize that as kind of a jumping off point for us. What we want to get is that we're always talking about curvature at a particular point, right? And then we're going to get a scalar value, right? So we're going to end up getting a scalar value or a constant value for that curvature at the particular point. So let's imagine that I've got this curve, okay? And so here's our curve, all right? And we have something that looks like that, okay? Here, and then let's do something that looks almost exactly like that, right? So we got a curve that looks something of that nature. Now notice, if I were to imagine that I've got a circle, okay, and that circle is moving along this curve, okay, you can imagine that we could actually fit a curve. That's not the greatest picture in the entire world, but we could fit a circle of about that radius in there, that curve. All right, so we've got that radius. Up here, on the other hand, the circle would be actually much smaller. So the radius would end up being much smaller. So here's a radius here, there's the little radius here. And up here, it would be even smaller, right? We end up having a much smaller circle even at that point. So what that means, and say here we might have a medium-sized circle. What that means is that here, this is the point of highest curvature. The most curve, the curviest, right? The sharpest turn. And then down here, this is the one that has the point of lowest curvature. And that's the basic idea of curvature. So whenever we're given the curvature of a line in space, what we're really being told is we're being told how sharp are the turns at that particular point, or the turn at that particular point, and that's what the curvature tells us. So here's our definition of curvature from the perspective of the work that we've been doing with vector-valued functions. So we're going to let C be a smooth curve in the plane, or a space given by R of S, where S is the arc length parameter. So remember that our function's been parameterized in such a way that whatever value S is, that is actually the arc length of our curve. So the curvature K at S is going to be K equals, and this is going to be the magnitude of the derivative of T, and remember T of T is going to be the unit tangent vector, parameterized for T. So T of S is the unit tangent vector, but parameterized for S. Okay? And what we're going to get is we're going to get T prime of S. So it's going to be the magnitude of T prime of S. Okay? Now, what you want to get here, and we talked about it earlier when we looked at like the qualities of vectors, the derivatives of vectors, we actually saw that if you take R, we have R of C, and we dotted it with R prime of C, we end up with that equaling 0. Okay? Meaning that, R prime of T, so you want to recall, we had that R of T dotted with R prime of T was going to equal 0. And so that means that R of T, if the magnitude of R of T is equal to a constant. So we have a constant value for the magnitude of R of T. So R of T and R prime of T are orthogonal if R of T, the magnitude, is equal to a constant. Okay? Now, the unit tangent vector, okay, the magnitude of T is actually equal to 1. So, what that means is that T prime of T, okay, is orthogonal to T of T. That they're actually orthogonal vectors. And so why that's going to be important is because we're going to take a look at curvature and see how that makes a difference. Okay? Basically, if we go back to our curvature, what you're going to see here is that this radius, the radius of this line, okay, is in fact going to be orthogonal to the tangent line. Okay, so if you imagine you've got this tangent line, Okay, there's the tangent line, wherever we're at. And then that radius here, that is going to be orthogonal to the tangent line. So this is t of t, and that orthogonal line, that's t prime of t. Okay, and its magnitude, the length of it, is going to be the magnitude of t prime of t. Okay, and in fact, in order to get the numbers right, we have to have it actually be t prime of s. So here's t prime of t of s. Okay, there's t of s, the tangent vector, and then that that radius is going to be then the length of the derivative of the tangent vector, and that's actually literally how we find our curvature. Okay, so that's actually our definition of the curvature. That's how we're going to be thinking about the curvature, right? It's basically, it's going to be how long is the radius of the circle that makes up the curve. Okay, the radius of the circle that makes up the curve, right? Well, this is actually kind of hard to find. It's a little bit of a pain in the butt. So when we're actually going to go calculate the curvature, we're going to utilize some different definitions or some different equations. So here are some more practical ways of actually calculating curvature. So we're going to start out with, we got curvature k is going to equal the magnitude of t prime of t divided by the magnitude of r prime of t dt, r prime of t. So first thing I want to get is I want to get that s of t, if you remember, is going to equal the integral, okay, from a to t of the magnitude of r prime of t, or r prime of u, du. And if we take the derivative of that, so we got d dt of s of t, which is equal to ds dt, that's going to end up equaling, using the first, the fundamental theorem of calculus, we're going to end up equaling, it's going to be the magnitude of r prime of t. It's just going to end up being the magnitude of r prime of t, assuming that actually, well, that, yeah, a is less than t. Okay, so it's just the magnitude of r prime of t. So remember that curvature is going to equal dt ds. Okay? So if I actually write this up, I'm going to get dt dt, so the derivative, so t prime of t, is going to equal dt dt, which is going to equal dt ds times ds dt, right, by the chain rule. So what that's going to mean for me is it's going to mean this. It's going to mean that dt dt divided by ds dt is going to equal dt ds. And if I go in here and I take its magnitude, all right, so that means that I've got the magnitude of dt dt divided by the magnitude of ds dt is thus going to equal the magnitude of dt ds, which is equal to my curvature. So consequently, this thing here, that's t prime of t. So that means my curvature, k, is going to equal, I got the magnitude of t prime of t. ds dt, remember, we just found that that's the magnitude of r prime of t. And so that'll then equal, right, my magnitude dt ds, and that's my curvature. And so that might actually be a lot easier, or that ends up being a lot easier to work with. Okay? So let's actually see an example of that. So let's suppose that we want to find the curvature for r of t equal to 4 cosine ti plus 4 sine tj plus 3tk, t equal to 4 pi over 3. So what I'm going to do, I first need to find, right, I'm going to have that my curvature k is going to equal the magnitude of the unit tangent vector divided by the magnitude, or basically the derivative of the arc length, right? Or the magnitude of the derivative of t, okay? So first I'm going to find t prime of t, all right? So t of t is going to equal, it's the unit tangent vector, and so it's going to be, it'll be negative 4 sine t plus 4 cosine t, or excuse me, negative 4 sine t, comma 4 cosine t, comma 3. So we'll take the derivative, and then we're going to divide that through, okay, by the derivative, because it's a unit tangent vector, divided through by the magnitude of this. So divided by the square root of negative 4 sine t squared plus 4 cosine t squared plus 3 squared. And so that ends up equaling negative 4 sine t, 4 cosine t, 3 divided through by, and this would end up being 16, 32, 35. Or excuse me, not 35, 16, 32, and then 41. So excuse me. So that ends up being, that'll be 16, this will be end up being 16 times sine squared t plus cosine squared t plus 3 squared. So that ends up being the square root of 25. And so consequently, our unit tangent vector is going to be negative 4/5 sine t, 4/5 cosine t, and 3/5. Okay? Now, what we're going to need to do, so that's t of t, we need to now find t prime of t. So t prime of t is going to then equal, t prime of t is going to then equal the derivative of t of t, and so that'll end up being negative 4/5 cosine t, negative 4/5 sine t, and 0. Now, it turns out that this right here, right, that's actually the magnitude of r prime of t, right? Because that's what we found. This is r prime of t. This is then the magnitude of r prime of t. We'll find it again anyways, right? So we've got r prime of t. Well, no, we don't need to find it again. That's it, okay? This is r prime of t, okay? So this, that root 25, is the magnitude of r prime of t. So consequently, we take, we've got t prime of t, right? We're going to need to find its magnitude. So t prime of t in magnitude is going to equal the square root of negative 4/5 cosine t squared plus negative 4/5 sine t squared plus 0 squared. Kind of trivial there. Which will just then end up equaling the square root then of 16 over 25, which just equals 4/5. Okay, because this is going to be a cosine t squared and a sine t squared. So there is the magnitude of t prime of t. So magnitude of t prime of t equals 4/5. We'll divide that then by the magnitude of r prime of t, and that means that this is 4 out of 25. Excuse me. All right, so what did we do? It's a bit involved, all right? We had to go find t prime of t. T prime of t is the derivative. Well, first we had to find t of t. So t of t is the unit tangent vector. You take the derivative of r, so that's r prime of t, divided by its magnitude. And just remember that the magnitude, that's the magnitude of r prime of t. We're going to come back to that. So 5, in other words. And then this gives us this value right here. This actually ends up being the unit tangent vector. Then we'll take its derivative. So the derivative of the unit tangent vector right here. Okay. And then to use our curvature formula, we're going to need the magnitude of the unit tangent vector. Okay. Divided by the magnitude of the derivative. Okay. So that gives me, in this case, 4/5 over 5, which is 4 out of 25, and that's the curvature of your function. So we have a second alternative formula, and this is the alternative formula for the curvature. It's going to be k equals r prime of t crossed r double prime of t, so that's double prime of t, divided by the magnitude of r prime of t cubed. Okay, and so sometimes this might actually come in pretty handy too, especially if taking the derivative of r of t is actually really easy. Okay, and we can find their magnitudes pretty easily. What we're going to need here in order to prove that this is the case is we're going to need first that t of t is going to be r prime of t divided by r prime of t magnitude. Okay? And in addition to that, we're also going to need that ds of ds dt is just going to equal r prime of t magnitude. So what that means is that r prime of t is going to equal, just doing some multiplication, it's going to be t of t times r, the magnitude of r prime of t, but that's just ds dt. So there we go. Now, if we want to find r double prime of t is just going to be the derivative of r prime of t. So it's going to be t prime of t ds dt plus t of t d squared s dt squared. And that's r double prime of t. So now, remember, we're going to try and figure out, we're going to say, okay, well, what's the curvature then, right? Okay, because we're going to see if we actually get something that equals the curvature. So let's find r prime of t cross r double prime of t. So that's t of t ds dt crossed with t prime of t ds dt plus t of t d squared s dt squared. Okay, we'll find the cross product of that. And so if you remember, we actually have an identity for working with these kind of derivatives. And so what we'll do first is, what we can do is we can distribute the cross product. So we'll start with that. So this is going to give me t of t ds dt crossed with t prime of t ds dt plus, and this will be then t of t ds dt crossed with t of t d squared s dt squared. Now these are derivatives, and so if you remember, we can also kind of pull the derivatives out, all right? So, or take the derivatives of the entire cross product. So we're going to get ds dt squared, or actually, excuse me, those are just functions, ds dt squared, and that's t of t cross t prime of t plus, and then this is going to be ds dt d squared s dt times t of t crossed with t of t. And those are just derived from our properties of the derivative of vector valued functions and the cross product. So now what I can see here is if you remember that t of t crossed with t of t, okay, that's going to end up being equal to 0. All right, that's another one of those values that we have. So consequently, this is going to zero out. This zeroes out, goes away. And so we're left with ds dt squared t of t cross t prime of t. Okay? Now, remember ds dt squared, well, what is that? Well, that's going to equal, so we've got t of t. ds dt squared is actually equal to r prime of t magnitude squared. And then that's going to be times t of t crossed with t prime of t. Okay? And if I rewrite this, remember that, so what we're going to do now is we're going to notice some things about this. Okay? One is that t, okay, and t prime are orthogonal. They're orthogonal vectors, okay? Because, if you remember, the magnitude of t is equal to 1, okay? And so consequently, if we have the magnitude of t is equal to 1 and we dot it with its derivative, we're going to end up with something with 0, and that actually implies that the two vectors are in fact orthogonal, okay? Or that we end up having orthogonal vectors, okay? So what that means is that the magnitude, okay, of t crossed with t prime of t, okay, is going to then equal t prime times sine of pi over 2. Okay? And if you remember, this thing here, the cross product is just equal to, it'll be equal to the, it's equal to the derivative, not the derivative, but the magnitude of each individual vector valued function times the sine of theta, right? Which is the angle between the two. The angle between the two of them is pi over 2 because they're orthogonal, Okay? And so consequently what we get here then is that the magnitude of t crossed with t prime of t is then just equal to the magnitude of t times the magnitude of t prime, okay, which ends up equaling, well, the magnitude of t is 1, all right? That's kind of cool. So the magnitude of t ends up being equal to 1 because it's unit, so this just ends up being the magnitude of t prime. So for us, that's interesting. Here's what makes it interesting. This thing here, remember this, is equal to r prime of t crossed with r double prime of t. Okay, so there's r prime of t crossed with r double prime of t. All right, and so its magnitude, the magnitude of r prime of t crossed with r double prime of t is going to equal, well, it'll end up equaling the magnitude of this because that's what we end up getting. So it's going to end up being ds dt squared t of t cross t prime of t magnitude. Okay, now we're actually, here's our cross product. We could actually just pull this piece out, the ds dt squared, okay, because that's just simply a derivative. So that's ds dt squared times the magnitude of t prime of t. Okay? Now, solving for t prime of t, what we get is now remember ds dt is r prime of t, the magnitude of r prime of t, excuse me. So this is actually going to end up being that t prime of t is going to equal this, r prime of t crossed with r double prime of t divided through by, and this is r double prime of t squared. So that's t prime of t. Okay? Now, remember, curvature, k, is equal to t prime of t, or the derivative, or the magnitude of, the magnitude of t prime of t divided by r prime of t. And so consequently, that means that curvature is going to equal, it's going to be this thing divided through by another r prime of t. So it's going to be r prime of t cross r double prime of t divided by r prime, not r double prime, but r prime of t cubed. Whew, that was tricky. Okay, so you might want to go through it. It's going to take a little bit of thought, process to kind of follow through with everything here. There's a lot of stuff going on. It's actually kind of handy to think through everything that we've been working through thus far into this proof, right? We've got, on the one hand, we have our definition of the tangent vector, okay? On the other, we have the derivative of our arc length, okay? We have an idea of like how to, using that product rule. We have those rules for taking the derivative of cross products and distributing across cross products. We have what happens if you cross a vector with itself. It ends up being equal to 0. We have this definition here, right, which has to do with, that's just simply that the cross product of two vectors is equal to the magnitude of one times the magnitude of the other times the sine of theta. Right, and this actually should not be a magnitude. That doesn't make any sense. Okay? And then in addition to that, we have this idea that t is a unit vector. So just to let you know, since t is a unit, that means the magnitude of t equals 1, just in case you forgot. Okay? Then we can pull out our ds dt squared, do some more substitution, and then go back to that definition of curvature. Whew! That one's brutal. That was fun. Good times. So let's use our alternative formulation, see if it might be easier here. We've got the same parametrization, or excuse me, the same vector valued function, r of t equals 4 cosine t, 4 sine t, 3t. So we're going to first find r prime of t. So r prime of t is going to end up equaling negative 4 sine t, 4 cosine t, and 3. And then r double prime of t is going to equal negative 4 cosine t, 4 sine t, and 0. Okay? Now, what we'll need to do is we're actually going to need, if you remember, the curvature k is going to equal the magnitude of r prime of t crossed with r double prime of t divided by r prime of t cubed. So we are going to need the magnitude of r prime of t. So let's find that. The magnitude of r prime of t is then going to equal, okay, this is going to be the square root of 4 cosine squared t plus 4 sine squared, excuse me, is going to be 16 sine squared t plus 16 cosine squared t plus 9, which equals root 25, which ends up equaling 5. Okay, we'll use that in a moment. Now what we're going to do is we're going to find the cross product. So let's find our cross product. I've got I, I've got J, I've got K. That is then going to be, I'm going to have negative 4 sine t, 4 cosine t, 3, negative 4 cosine t, negative 4 sine t, and 0. I am going to start out with, right, we'll end up with 0 plus, so this is going to be 12 sine t, and then comma, and this will then be 12 cosine t, and we will also end up with 16 sine squared t plus 16 sine squared t plus 16 cosine squared t, so just 16. And that is r prime of t cross r double prime of t, okay? The magnitude of this is going to end up being just, well, we'll get the square root of, and this will be 12 squared sine squared t plus 12 squared cosine squared t plus 16 squared, okay, which equals, this will actually equal the square root of 400, which equals 20. Putting that into our curvature formula, that's going to be 20 over 5 cubed, which ends up equaling 20 over 125, which, if we divide through by 5, is going to give me 4 out of 25. And that's my curvature, which was my curvature before. Good news! Okay? Now, by the way, this is a circle. Okay? This is a circle. It's a circle of radius 4, and so if you think about it, on a circle, the curvature is always the same, right? It's always going to be the same. And so that's one of the reasons why the curvature for this particular vector valued function ends up being equal to a constant value. They aren't always. In fact, we'll see an example right now. So this is going to complete our discussion of curvature. You'll notice the big things about curvature is to understand what curvature is. All right. So the curvature is the amount of basically turn inside of a curve at a particular given point, or just in general on the curve if we happen to have a constant curvature. One thing that we want to get is we want to get that a curve can have multiple different curvatures. All right. And we might actually have to figure out what that value is for a given s or a given t. All right. That happens all the time. We have 3 alternative ways of actually defining curvature, and so you might find that the second and the third ones are actually the easier to work with. We are going to use that first one to do more work in proof and to talk more about like kind of the concepts that go in with talking about vector valued functions and the like. But for the moment right now, when you're actually calculating curvature, you might find the last 2 to be the most handy and helpful. All right, this completes the lecture.